because they're listening.
It doesn't
We're in chapter 14, page, I don't know, but theorem 14:11. How much do I need to remind you of all the things that we were doing?
Next to none.
Okay.
Start again. Okay, chapter 1.
Okay, so what we're talking about in general is group actions, right? Group action is where every group element is actually a permutation of some set. We didn't say permutation, but it follows from the definition that it has to be a permutation, it has to be something that just moves the set around rather than can't identify things, and it can't leave things out of the image and stuff like that, because you need inverses, because the inverse of the group element has to be the inverse mapping in that transformation. So it follows that the transformation that is doing something to the set has to be a permutation, has to be injective and surjective. Otherwise, it doesn't have an inverse. So we were talking about actions. Then there was what we need for this. Prove yet? I can't find the proof. Is the notion of an orbit. So what is an orbit?
What a number in a set was bounded to. Sort of like, in the examples we were doing, it was like 1, 2, 3. So 1 was bounded to 2 and bounded to 3. And then like, it could go to 4 or 5. Bounded. Yeah, there's like,
yeah.
The options of what it could be mapped.
Yes, exactly. So like where I have my picture, this is the group, this is the set that it's acting on. And so X can be moved to itself, of course, by the identity mapping, so it can always be mapped to itself. And then there are a bunch of other elements that can be mapped to. And we prove that the orbits, well, I actually define the orbit as equivalence classes. So this chap can be moved to that one and that one as well. It's symmetric and transitive as well, so you can move that to that and that to that, and by the composition of these two mappings, which is what you want the products of the two elements to do, can be moved. So like everybody can go to everybody else in that little orbit. And nobody can go anywhere else then within the orbit. Okay, that is the basic. Now, then we had a second thing, was the stabilizer. So look at all the group elements that leave X in place, don't move it anywhere else. Map to X. It's a subgroup. It proves it's a subgroup. So it can't be just any old set of elements in G, but it has to be a group. And then we have this theorem which is saying, okay, and then we had this remark by Jordan, which was very useful, which I'm really very grateful for. And Jordan suggested that because of the group, etc., and all the symmetric properties of the group, all the orbits should be the same size. But no. And the crucial difference is inside the orbit is that the number of elements of the group that fix X, so the stabilizer of X, can be different. So it can be a different subgroup in each orbit. Okay. And this theorem is basically saying that the size of each orbit is equal to the index of the stabilizer in G, which, I should add, is the size of the group, as we know from before, divided by the order of the group, divided by the order of the stabilizer. Okay. In particular, not only we know from Lagrange's theorem that every subgroup has order which is a divisor of the order of the whole group, but also every orbit size has to be a number which divides the order of the group. If it's a finite set finite group acting in a finite set. The assumption. So, proof. The proof is crucial. So, how do we prove this? Okay. What's the definition of the index? Exactly. So, the index is the number of left or right, doesn't matter. What do I do? Here, left cosets. There's the same number of left cosets as there are right cosets, so each of them can be taken of Gx. Stabilizer in G. Okay. So how do you prove that certain things have the same size sets? Typically. Pardon?
How do we prove what?
That two sets have the same size.
You create a bijection.
Exactly. You've learned something.
Just one thing.
So we show in.
Do you want me to say every time I ask a question, I've got that one response?
I mean, collectively, you've learned something. The plural of you is you guys in American English, but in British you can say whatever you want. We show a bijection between OX, and so that's the orbit, and the set of all cosets of Gx. Okay. How do we do it? Bijection, I'll call it phi. Readable? No one's watching. We can't confirm that it's readable for them. There's strange lighting. Do you want these lights on? Or is it okay?
Yeah, so good.
So for any y in that orbit, right, f phi y will be, now what I want is a coset, so I want all the G in G such that G sends x to y. Okay, x is fixed, whatever, x is what we start with. Right? So that's one element, you pick it, it can be any element, of course that's why it's called x, but it's one which is always the same throughout the whole thing. That's like thing. Now for any y, now I want this bijection here, which I've already started doing. And to any element, you assign it all the little g's which send x to it. And I'm hoping that that's a coset. So what do we need to prove? First, that it's a coset. So we prove, well, we look at something that is in the set, and we want that the whole thing is actually the coset defined by this. So the coset is G times everything in the stabilizer. And what's my proof? So we want to show that they're equal. If we want to show that two sets are equal, a good way of showing it is usually what? I repeat the question. Shall I repeat the question?
That one's bigger than the other, and then that one's bigger than that.
Yeah, exactly. So So I put it as show the subsets of each other. Okay. So if you want to show that something is a subset, you take an element which is in there, any odd element in there. So why is it in phi y? Well, because it maps x to y. So gx is y. G dash x, sorry, is y. So I've carefully created this. So G inverse y is G inverse G dash. Now I'm not sure whether you can distinguish the inverses from the dashes. Maybe I shouldn't use dashes, but well, there we go. This is
G dash inverse.
It's G.
But they need if
no, G.
inverse-
That's G inverse y.
G.
Oh yeah. I'm gonna wait. If you usually correct yourself.
What am I doing?
Um,
Oh no, this is supposed to be x.
oh.
Yes. Now. What am I doing? I got lost. Oh, and so this is x. So okay, this is x. No, but I should have started like yeah. Okay, it's time to fix it properly.
I'm waiting. I'm gonna wait. This is gonna laugh, and Helen hates him for it.
G inverse G
Yeah.
dash
Feels here a lot.
x. Okay, so right. G sends x to y. Because I told you so. No, G is in phi y, so G sends x to y. So G inverse sends y to x, because inverses send things back where they belong. G dash is also in phi y, so G dash x is y. So G inverse y is x. And y I can replace with G dash x. So I get x is equal to G inverse G dash x. And therefore, G inverse G dash is in the stabilizer because it sends x to x. And therefore, if I multiply this by G, this whole thing, I get that G dash is in GGX. Okay, so this proves one of the equations. It's one of the subsets. Okay? Now you believe me? No, I'm just reading your fleece.
Of course I.
Okay. Now, if G dash is in GGX, then, and this is getting worse. I don't know why I was. So what does that mean? That means that G dash can be written as G times some element G bar.
Oh goodness.
which is in the stabilizer.
So G dash is now.
And so, what I'm trying to do, what I'm trying to prove is that G dashed is in the phi thing. Right?
You said G dash.
That was assuming.
No, we've
on,
already
like,
finished
That
it.
was assuming.
I was assuming it in part A. Now in part B, I'm assuming that it's on the right-hand side, and I'm trying to prove that it's on the left-hand side. So if G dashed is in the right-hand side, because of the definition of the coset, it can be written as G times G bar, some G bar from stabilizer. So now I'm looking at what G dash does to X, because that's what I want to show that this is Y. So I rewrite it as G bar X. Now what is G bar X? X, because G bar is in the stabilizer, so this is the same as Gx, and Gx is the thing that was defining something.
Phi y.
Phi y, there we go. So no, G is in phi y already, we already know that. So this is X, and therefore G dash is in phi of y. Good. Okay,
So
you need some time to process it.
right, so it goes in.
But when processing it, you always think of, oh, this is what I want. Oh, this is how I'm getting it. It's quite straightforward.
Yeah.
The proof is wrong in the book, so I had to invent it myself. So it can't be very hard to do. Okay? Now is I bijection. So bijection again, that's A and B. So if GGX is a coset, then
Yeah.
what's 5GX?
It's fine.
It's-
Okay. So what is 5GX? Okay, so what is this? This is the set of everything in G which sends X to GX. G is one such thing. G does send X to GX, obviously. So it is one of these sets that contains G, and we already know it's a coset, so it can't be anything else than the coset of G.
So far is answer.
Okay. Is it too much pure maths for Friday in the afternoon?
That's
Equals G.
that's an element acting on every element in the stabilizer.
Oh, it's not acting, it's multiplying. Yes, because it gets worse when the action will be by. So, okay,
For both.
so So what I want to prove is that it's a bijection, which means it's injective and surjective. So surjective is, okay, I want to show that every coset you get as an image. If you pick a coset, take any element in that coset, and let that thing, that element G act on X. And what you get, okay, so it's kind of, you want the coset of G2. Okay. What is mapped onto the coset of G2? Well, the element that X jumps to by G2. That's the idea. Okay. Now you want that. Now the second thing is you don't want two elements here mapped onto the same coset. Quite fine, and that's kind of clear. So if that means that if you get two elements from the orbit, G1x and G2x, and they go onto the same thing. Then, oh God. What do I want? I want so it's kind of so this is the set of all G's that map X to Y. So it must be the coset of G1. So this must be the coset of G2. So the coset of G1 is equal to the coset of G2. So that means that what do I want? I don't know. Then G1x equals G2x is clear. Okay. Okay. Any questions? I can't think anymore. I put it's clear in my notes, so it must be clear. It must have been clear to me. It must have been clear to me at some point. Okay, next. Let's see. It's clear.
No.
Clear, but I'll make it asked.
It's clear, right, apparently. Okay, thank you. Thank you. Good.
I think I'll fill in the blanks at some point.
Yeah.
Okay.
As long as it's during the exam, then that's fine.
Yeah, okay.
It comes in. This is why it's clear.
So next section. We need to finish this. The class equation.
Why is it clear?
Christian said.
Okay, I'm putting the exam on the question on the exam. Why is it clear that?
Awesome.
I promise.
I have
You can take it.
I have an IOU in my old book of yours. It says Jan promises that this works or something.
Didn't we go over it later though?
I can't remember.
Did we what?
We assumed something was
Yeah,
true.
because they said so.
Jan said so.
Yeah.
And then we proved it later.
I think it proved it.
Possibly.
I hope so. Okay, what is the class equation? Okay, so let G in X. Okay, we always start by G acting on X. Now,
Is this an example or a definition?
It's a section name.
Section name, floating point.
It's at the top of the page. It's huge.
Oh, good. All right, so it's not really much of anything.
so so define xg to be, so basically what this is all the elements of X whose orbit has size 1, okay, that sit in the orbit by themselves. Well, we sort of put them to the side because for later applications we need to put them to the side. But we don't have to. So this is the set of all X's such that all G's, all the elements of the group fix it. Okay, so it doesn't get moved ever. So its orbit is X only. Yeah, so we'll put them on one side. So the class equation is really stupidly easy, right? So size of the set X is the sum of the sizes of all the orbits. Because every element is in exactly one orbit, except here it's put in a slightly fancy way. So you look at all the elements you count all the elements whose orbit is size 1, and then you add to it, I don't know why, for a good reason, for later use, we want to put it like this. So you look at all the other orbits and add the sizes of all the other orbits together. Okay. So what you're doing is look at how many elements have orbit of size 1, and then add the sizes of all the other orbits to it, and what you get is the number of elements.
The size of the orbits of one, they could just be included in the sum.
They could be. Yes, that's what I'm trying to say. That we will later do some applications of this where it's useful to have it in this form. Okay, so I should say what but yeah, you're exactly right. We could do all the things in one. It would be perfectly all right. So where xk dot xn are representatives of the distinct orbits, non-trivial, okay, so distinct non-trivial orbits. Non-trivial means size is not 1. So a trivial orbit is the one that only has one element, and all the non-trivial ones. Yeah. Okay, now, what am I saying? Okay, so now we're going to use it for something. That's it. I mean, there's no proof. I mean, there's no, well, it's not, nothing to prove. Right? It's just,
Classification, just an application.
we know that orbits are. Now there is a definition. The center of a group G is something called ZG, which is all the elements of G such that xg equals gx from this symbolizes the end of the definition. Okay. So the center is the set of all elements that commute with everything. Look at an element, and if it commutes with everything, you put it into the center. Look at another element, and if it commutes with everything, you put it into the center. Now, what we discussed, perhaps on Friday, quite a lot, was a group acting on itself by conjugation. Right? So G acts on G by conjugation, which means that, what does it mean? So when you get G from G and X from also from G, because X is equal to G. Now let me put it the right way. So you want GXG inverse. Okay. Now this is starting to be counterintuitive. Okay, we've got that. So think of you've got these elements, and then whatever they are, G acts on them by conjugation. Now, so do you see any connection between this? Okay, when I say that for all elements of G, xg equals gx is the same as for every G in G, x equals gxg inverse. Okay. Can you see the connection now? So the center is that set in that particular action. Because if we're looking at all the x's, such that every element of G is in place when it acts by conjugation. Okay. So now the center is there. So okay, and then we should say that the non-trivial orbits of this action are called conjugacy classes. Okay. And the stabilizer of xi, which is not in the center. But what's the stabilizer of things that are in the center?
anything, can it, if they're already in the centre? One thing we said last week where you can't move anything that's already at 0.
I'm lost. Oh,
Keep going.
Okay, exercise. What is the stabilizer of an element of the center? Okay, what is the stabilizer, how it's defined? It's all the elements of the group that leave it in place in an action. Okay? So what's the stabilizer of an element of the center? And these things are not easy the first time round. But they're not even easy the second or third time round, so that's why. Oh my goodness, we haven't covered. Okay, we're supposed to cover everything, and we haven't. Okay. So the stabilizer of the center is, of an element in the center is the whole group G, because that's everything keeps it fixed. So everything is in the stabilizer. But if it's not in the center, then the stabilizer is called the centralizer. Of its own. Okay, so you could wonder whether we're inventing new names for the same thing, but that's because historically the centralizer was probably defined before the stabilizer. So we're going in a bit of a roundabout way to those notions, and that is because it's quite nice to explain them in this way. But at least that's what the author of the book thinks. And I'm more agree than not. Okay, so this is C. All right. What's the centralizer? Well, it's all the elements of G, such that that action. So you can say that Xij equals G. So the centralizer of an element is all the group elements that commute with it. Right. The centralizer is the whole group. Then that X is in the center. Okay, let's not spend too much time. Okay, so now when you look at the class equation, actually what is actually called the class equation is that equation for the conjugation action. Okay, so the class equation is so the size of X, now G is acting on itself, so the size of G is, well, X of G, we said that was the center. And then you have to add, okay, and what's the size of the orbit? We know that the size of the orbit is the index of the stabilizer, okay? So what we're adding is the indices of all the centralizers xk, xn are representatives of the distinct, what do I put there? Non-trivial orbits. Well, non-trivial orbits are now called conjugacy classes. Okay. They're quite demanding. Don't despair. You just need to process it later again. Okay? There's not much going on. Like it's mostly introducing new names for things and saying that, oh, this is a closet. She's always says something. Okay, so there are examples 1412 and 1413, which you can read, but they're not very exciting. Example 1414. Sn. So what are the conjugacy classes in the symmetric group?
Okay.
So do you remember cycle decompositions of permutations in the symmetric group?
Decompositions are conjugated along with the cycle decomposition.
I've not finished the sentence yet, so that doesn't mean it. But yeah, I'm just asking whether you remember the cycle decompositions. It was like, 1 goes to 2, 2 goes to 7, 7 goes to 1. Cycle finished.
Yeah.
So you decomposition in this case, what we mean is disjoint cycles, because there's plenty of ways how you can write a permutation as the product of some cycles. For example, you could go for transpositions, which was the way how we arrived at the sign of the permutation, whether it was odd or even. But the most concise way is where you don't repeat any element. Okay, so that's basically what the permutation is like. One cycle, another cycle, another cycle. And so conjugation leaves the lengths of these cycles. So it might swap the elements among the cycles somehow, okay, but it never changes the lengths of the cycles. If you only does, I have the same length. Oops. Okay, so when you get to, for example, within an example, okay, when you take 1, 2, 3, 4, 5, and so this is conjugate to 2, 4, 3, 1, 5, because the cycles have length 2 and 3. It's just a matter of finding the right thing that when you apply it from one side and the inverse from the other side, you get the other one. But, so this is an example. So what else do I want to say about this example? Oh, so how many, okay, so when you look at S3, for example, what are the conjugacy classes? Well, there's one where there's one cycle of length where these are all cycles of length 3. So you get 1, 2, 3, and 1, 3, 2. and then go any other ones. Then there's a 2 plus 1, which would be 1, 2, 1, 3, and 2, 3. That's 3 permutations. Okay, and then there's 1 plus 1 plus 1, and that's the identity.
And there's the 6, yeah.
So that's the center is true in this case, it's just the identity. And the class equation is that 6, which is the number of permutations of 3 things, is, well, 1, which is the size of the center, and then you have 3 and 2 in the conjugacy classes. Okay, so this conjugacy class is 3 elements, and it's 2. I should put them in a set because it's actually. This is the center. Yeah, we've done 2 pages. One selection, 2 pages.
Yeah, that makes a little bit more sense. It's just the whole jargony part.
Yeah. You have to look at the examples. So you can look at more examples in the book, but I'm not going to do it more now. So that's all we have time for now. Tomorrow, what we're going to do is, well, there are theorem 14, 15, 14, 16, basically. There are just some consequences of class equation. Would say that if you have, well, the first one is that if you have a group of prime power order, then the center is non-trivial. Okay, so it can't be just like 1. But this is not prime power order. It's 6, so not a contradiction. And another corollary is that you have p squared order group, so the second square of a prime, and it's abelian. So prime order is abelian because it's cyclic. And tomorrow we'll see that prime squared is also abelian, even if it doesn't have to be cyclic.
Just trying to look at the first few prime square patterns.
And then what we're hoping to get is what's called orbit counting lemma. And that's a lemma which tells you how many orbits there are.
What, like automatically, or?
Kind of. And then next week we'll do applications of the orbit counting lemma. So I hope we can prove it tomorrow. So the applications are basically, so for example, I think it's in the book. The first example is how many ways can you color the vertices of a square with, say, 3 colors or 2 colors. Okay. So of course, if it's 2 colors, then you have 2 options for each vertex. So you'd say 16, but then some of them are indistinguishable. So if you only color 1 white and the rest black, or blue and red, then that's the same as if you color this vertex blue and the rest red. So you can't, because so up to symmetries, how many ways, and that is the number of orbits of the dihedral group acting on the square. In this way. So the counting lemma will give us the number of different ways, essentially different ways, how to color things and so on.
And there's another. That's why we want to do the content. Okay.